Okay, let's continue our talk about orbitals. I believe the last time we talked about an s orbital, which remember when L is equal to 0, that's an s sublevel. The only allowed value for m sub L would be m sub L equals 0. So that means there's one s orbital and an s sublevel. So therefore, if I drew you a picture of the s orbital, I have drawn you a picture of the entire s sublevel. And we looked at that and we noticed that it was spherical in shape. And we talked about nodes inside and nested spheres and all that. But really all you got to know is that an s orbital is spherical in shape. Okay, and it's a region of space where the electrons are most likely to be. And that is unfortunately the best we can do, at this given point in time. A 1s is relatively small. The electrons spin their average distance from the nucleus very close to the nucleus, low in energy. A 2s is larger, a 3s is larger still, and so on and so forth. And that's the main difference between them. Okay? All right, so let's go to the p sublevel. That's L equals 1. The allowed values there would be m sub L can be -1, 0, or 1. So what that says is there are 3 p orbitals in a p sublevel. So what does a p orbital look like? Well, a p orbital kind of has this dumbbell shape to it. Okay, you've got a lobe of electron density over here, and you've got a lobe of electron density over here. This side over here is the positive side. This is the negative side, or this, depends, you call it the positive, negative, I guess it doesn't really matter. But when we say positive and negative, we're not saying that an orbital has a positive charge and a negative charge. The positive and negative are just the algebraic sign of the wave function. And that comes into play when you start worrying about orbitals interacting with each other. Are they going to interact with each other constructively or destructively? It goes back to the wave stuff. So don't get too worried about the red and the blue or the plus or the minus or this or that. Basically, you've got a lobe of electron density here and a lobe here. All right? And that's a p orbital. And of course, any orbital always holds 2 electrons. So I can fit 2 electrons inside that orbital. Does that mean one of them is here and one of them's here? No. They might both be here. Might be both be here. Might be kind of here and here at the same time. Electrons have wave-like properties. And so, yeah, things get a little weird when you get down to the world of the quantum mechanics. They're kind of ghostly, sort of. The best we can do is we can say somewhere within this region of space, I can fit 2 electrons. And that's it. A 2p, of course, there's no such thing as a 1p, only energy levels 2 and higher can have a p, is a relatively small lobe, like this. A 3p would be larger lobes. The electrons spin their average distance from the nucleus further away. 4p larger still, and so on and so forth. Okay? All right. Well, we said there were 3 p orbitals in a p sublevel. So what do they look like? Well, when you have orbitals within the same sublevel, these are the requirements. The first requirement, and the main requirement here, I guess, would be that your orbitals have to be degenerate. All right, and when we say our orbitals are degenerate, we are saying nothing about the moral character of an orbital. What we're saying is they have to have the same amount of energy. In other words, an electron's just as likely to go in one as the other. Okay? So, for the p orbital system, they also have to be orthonormal. Normal means the wave function has to be normalized. The probability of finding the electron within the entire universe is 100%. Not 50%, not 150%. Don't worry about normalizing wave functions. That's way beyond the scope of this course. We don't have to worry about that. The ortho part, however, for the p orbital system means they have to be orthogonal. And orthogonal means, in simple terms, at right angles to each other and not overlapping. We'll go with that. So, how can I draw another p orbital that looks just like this, is at right angles to it and not overlapping? Well, I can do it like this. See, up and down, like that. Okay? This is lined up along the x-axis, so we call this the p sub x. This one, normally we reserve the vertical axis for the z in a x, y, z coordinate system here. And so this would be the p sub z. Okay? And the only difference between the two is just the way they're oriented. This one's turned this way, that one's turned that way. All right? Same size, same average distance from the nucleus, so same energy, it's just one's this way and one's kind of that way. All right? But we said there were three. So how can I draw another one at right angles of these two but not overlapping? Well, remember that electrons and the orbitals they occupy are three-dimensional, just like you and me. So I can go this way, I can go this way, but I've got a third dimension I can work with. Imagine a lobe that's coming straight out at you and another lobe going straight back away from you. And that's your third p orbital. And that's lined up along the y-axis here, so we're going to call it the piece of y. This holds 2 electrons as well. So I can put 2 electrons here, 2 electrons here, 2 electrons here, so I can fit 6 electrons in a p sublevel. 2 electrons go in an s sublevel, because there's only one orbital. 6 electrons go in a p sublevel. What does it look like when you put them all together? Well, it looks a little something like this. Imagine a jack, okay, or a three-dimensional coordinate system if you're more mathematically minded. And that's what your p orbital system looks like. You've got one going this way, one going at you here, straight toward the camera and back out, and then you've got one going up and down. All right, 2 electrons in each of those, 3 times 2, 6 electrons in a p sublevel. And that's what a p sublevel looks like. A 2p is relatively small, a 3p is a larger one, and 4p is larger still, and so on and so forth. Make sense? Okay, well, what comes after p? Well, that would be d, right? Okay, so what does a d orbital look like? Well, if you'll remember, we said that the orbitals had to be degenerate. In other words, they had to have the same amount of energy. Is there any requirement that they have to have the same shape? No, there's no requirement. All right. Let's say, for example, I asked you to give me 4 cents in change. How would you do it? Well, you'd probably give me 4 pennies, right? Is there really any other way to make 4 cents in change? Well, no, not really. That's pretty much it. But what if I asked you to give me $1.67 in change? How many ways could you do that? Well, you could give me 167 pennies, I guess. You could give me, what, 4 quarters and 6 dimes, a nickel and 2 pennies. You could give me, what, $1.67, 16 dimes, maybe, and 7 pennies. I mean, there's a ton of different ways you could come up with $1.67 in change. Do you see the more money we're talking about, the more different types of coins I can put it together and get the same amount of money? So if I said, give me 6 cents, well, you could give me 6 pennies, you could give me a nickel and a penny. If I gave you a nickel and a penny and you gave me 6 pennies back, would we be even? Yeah, it would be even. Okay? Well, by the time you get up to the d orbital system, it turns out there's 2 different shapes that give you the same amount of energy. One of those shapes is kind of a 4-leaf clover type shape. So, for example, kind of looks like this. Now, I've got 4 lobes here on this d orbital, but I can still only fit 2 electrons in there, even though I've got 4 lobes. Any orbital always holds 2 electrons, any type of orbital. S, P, D, F, G, SP, SP3D. If it's an orbital, 2 electrons, always. Okay? There are 4 of those, okay, and they look something like this. So here are my d orbitals. So you've got one lined up this way, you've got one lined up this way, you've got one lined up that way, and then one that way. Okay? And the only difference between my 4 d orbitals of that particular shape is just the way they're oriented. One's this way, one's lined up that way. But it's the same shape, they're just turned differently, kind of like my p orbitals. Okay? This is your dxy, which is kind of lined up in between that xy axis there. This is your dxz, this is your dyz, and this is your dx squared minus y squared one. You don't have to know that, but that's just what they call them. Okay? The other one is a shape that looks something like this. And this is your dz squared orbital. And I like to call it the Saturn of p orbitals. It looks like a p orbital, sort of, but you got this ring of electron density around the middle. And you can fit 2 electrons in there. And this orbital, although it's a different shape, is exactly the same energy, equally likely to be populated as this orbital right here with the 4 lobes. It's like 6 pennies and a nickel and a penny. Same amount of money, just a different way. There are 1, 2, 3, 4, 5 d orbitals in a d orbital system. Each one holds 2 electrons. So these 4 that hold 2 electrons, there's 4 of those. That's 8. One of them shaped like this. That's 2 more. 10 electrons in a d sublevel. See? When L is equal to 2, what are the allowed values for M sub L? -2, -1, 0, 1, and 2. 1, 2, 3, 4, 5 d orbitals in a d orbital system. I can fit 2 electrons here. I can fit 6 electrons in a p orbital system. I can fit 10 electrons in a d. Are you seeing a pattern? Notice it's going up by 4 each time. Why is it going up by 4 each time? Well, the reason it's going up by 4 each time is because each successive sublevel has 2 more orbitals. And we said each orbital can hold 2 electrons. So if I got 2 extra orbitals, 2 electrons, 2 times 2 is 4. And that's why it keeps going up. It's not the orbitals that hold more electrons, it's the fact that you have 2 more orbitals each sublevel. See, look, I know it's confusing, but it is consistent. It does make sense if you can somehow unwrap it all. It's consistent. You have a fighting chance of learning this. Okay? All right. I'm even going to try to draw all that together because I just can't. There's no way. If you can somehow manage to put that together in your head, then, you know, congratulations. But just don't have the artistic ability to do that. All right? Okay, well, let's go one more real quick, and then we'll move on. Let's talk about an F orbital system. Okay, so F orbital system, if 2 and higher, if all of them can have an S, if 2 and higher can have a P sublevel, 3 and higher can have a D sublevel, then 4 and higher can have an F sublevel. See, it's a pattern. Okay, containing, how many orbitals do you think there are? Well, 7. See, 1, 3, 5, 7. See, pattern. 7 F orbitals, each containing how many electrons? 2 electrons, for a total of 7 times 2, 14 electrons in an F sublevel. See, there's a pattern here, so you can just kind of continue on from there. So what do your F orbitals look like? Well, I'm glad we have the book, because there's no way I could draw these. But yeah, basically you get this 6-lobe shape here. And then it looks like you got an 8-lobe over here. Well, no, there should be a 6-lobe shape. I wonder what's going on with that little guy right there. But, oh yeah, okay. No, I think they made a mistake on that actually right there. That probably shouldn't be there. But yeah, you got these 6 lobes here. And these are all kind of lined up differently. Okay. But here's this FZ cubed orbital. And notice it looks kind of like your DZ squared, only instead of having 1 ring of electron density around it, you got 2. So that's kind of cool. But yeah, I mean, look at all these lobes. 1, 2, 3, 4. Well, maybe there was 1 there. 4 there. Looks like you got a 6-lobe shape, and then you got some 8-lobe shapes here as well. So yeah, that's what your F orbitals look like. You know, interesting there. F orbital chemistry is, someday I'll do a little talk on that maybe, but not today. But yeah, there's some interesting things about F orbital chemistry there. Maybe that may be a chemistry club talk someday or something like that. But yeah, that's what your Fs look like, kind of like that. And yeah, of course, we're not going to try to put those together, right? Can't do that. All right, but notice the pattern: 1, 3, 5, 7. Okay, and then what do you think a G would be here? That's the next one. Well, it'd be 9 G orbitals holding 2 electrons apiece, for a total of 18 electrons in a G sublevel. All right, so yeah, see, it's a pattern. All right, and that's what the orbitals look like, and they are regions of space where the electrons are most likely to be. Okay? All right, so we've got our energy levels, which are divided up into sublevels, and my sublevels are divided up into orbitals. So again, it's kind of like a parking lot, which is divided into sections, and those sections are made up of rows. Okay, well, what are the rows made up in a parking lot? They're made up of what? They're made up of spaces, right? You'd be in row 17, space 3. All right, well, it turns out there's a fourth quantum number that the electrons have as well. If I have electrons with the same first quantum number, they're in the same energy level, or shell, whatever your book is calling it these days. If you have electrons with the same first two quantum numbers, they're in the same sublevel. If I have electrons with the same three quantum numbers, they're in the same orbital. How many electrons can I fit in an orbital? Well, just two. So I need a fourth quantum number to distinguish between those two electrons. All right, and that fourth quantum number is something called m sub s, which is called the spin of the electron. All right, how many allowed values do I need for m sub s to give every electron its own set of four quantum numbers? Well, only two. See, I just give one of them one value, give the other value, and there you go. Every single electron has its own set of quantum numbers. The allowed values for m sub s are plus 1/2 and minus 1/2. The 1/2, but essentially because it's a fermion, we won't go any further than that. We'll talk about the plus and the minus. Okay. Spin is a certain intrinsic quantity that electrons have, and nuclei, particles actually have as well, that doesn't really have a nice concrete analogy that I can give you, that works up here. The best I can do is it's kind of like a ball spinning, or a top, or a globe that's kind of spinning on an axis. All right, so let's say, for example, you've got a globe. There's really two ways you can spin that globe. You can either spin it clockwise, looking from the top, or you could spin it counterclockwise, and that's pretty much it. Okay? Well, an electron in certain circumstances, especially in a magnetic field, electrons behave as if they were charged particles that were spinning. Are they really little tiny globes? No. But they behave as if they kind of were in certain circumstances. And that gives rise to the concept of what we call spin. All right? Spin, electrons are usually kind of randomly oriented, but when you observe them, they always collapse into one of two cases. Either what we call spin up or what we call spin down. All right, so what does that mean? Well, in physics, there's something called the right-hand rule. And sometimes you'll watch people taking a physics test, and they're doing this, and then they're doing that, and just, they look like they're, somehow they're going into some sort of fit from the, too much physics overload there. Their hands are cramping up and stuff like that. What they're doing is they're applying something called the right-hand rule, which says, among other things, if I take a particle that's rotating and I curl my fingers in the direction of the rotation, my thumb on my right hand shows me where the angular momentum vector is pointing. So let's say, for example, I've got a globe and I'm spinning it, let's say, counterclockwise, looking from the top down. Well, what I'm going to do is I'm going to take my right hand, I'm going to curl my fingers in the direction of the rotation. So counterclockwise, looking from the top down, would be like this. My thumb shows me where the angular momentum vector is. Okay, notice my thumb's pointing up. And so that is what we call spin up, or the plus 1/2. If I spun it clockwise, curl your fingers in the direction of the rotation. Which way is my thumb pointing? Down. And so that's where my angular momentum vector is pointing. And so we call that spin down, or minus 1/2. So an electron can either have a spin of plus 1/2, or it can have a spin of minus 1/2. And that's it. It's like heads and tails on a coin. You flip the coin, it either comes up heads or tails. It doesn't land on the edge. Same way with electrons. Give one electron in that orbital a +1/2, give the other electron in the orbital a -1/2, and there you go. All of your electrons now have their own set of 4 quantum numbers. All right? So it goes energy level or shell, composed of subshells, sublevels, that's L, which is composed of orbitals, that's M sub L, it's your 3rd quantum number, and within your orbitals, an electron can have 1 of 2 spins. All right? It's a lot to hang on to, I know, it's very abstract, but if you think of it in terms of a hierarchy system, I think it's easier for you to wrap your mind around the whole thing. So do the best you can. Stare at it until you go blind. Hopefully it will make sense before test day, right? Okay? All right. Well, what does all this have to do with chemistry? You might be asking yourself. Okay, it's nice to know they're there, I guess, but does this really do anything for me here, practically? Well, yes, it does. Okay. Now that you know something about the electronic structure, how the electrons are arranged around an atom, now you can start writing what we call electron configurations. All right, and in electron configuration, what you do is you indicate by a superscript the number of electrons in each sublevel. All right? So essentially what we can do now is we can say, okay, well, I've got myself a calcium atom. How are those electrons arranged around that calcium atom? You know, before what we said is we could say, I've got 20 electrons out there in that calcium atom, an electron cloud somewhere outside the nucleus, and that's the best I can do. I believe I told you I could do slightly better than that. Well, here we are. We're going to do slightly better than that. To get the electronic structure of a particular atom, you need to generate something called the order of filling. All right, and the order of filling essentially is a list of the sublevels from lowest energy to highest energy. All right, think of it this way. What we're writing here is we're writing what we call ground state electron configurations. In other words, the electrons in their lowest energy state, which is the way you find them 99% of the time. All right. So it's kind of like, well, it's kind of like parking cars. So let's say, for example, you're going to class. You're going to lab today. Where are you going to park? Well, I mean, over by the SHAP Center, there's a ton of parking spaces. Big, giant parking lot out there. Are you going to park out there? Well, what about the administration building? How about over there? Where are you going to park? Well, probably over in the Fox Science building lot, right? Why would you do that? There's more spaces over at the SHAP Center. Well, because the Fox Science building parking lot is closest to the building, and you don't want to have to walk, right? So let's say you came to lab, and that entire parking lot was full, completely full. What are you going to do? Go home? Well, maybe, but I would advise it. Well, you'll probably look for another parking space somewhere. Maybe you'll check over there by the tennis courts, right? See if there's a space there. What if that's full? Well, maybe you go over there by the health center over there, and you park over there across the street, and you do that. But what you do is you keep looking for a parking lot, the next closest available parking lot, and then maybe the next closest. You may end up over at the SHAP Center by the time it's all said and done. Who knows, right? But that's certainly not going to be your first choice. Well, electrons are the same way. They prefer to be in the lowest energy state possible. So what is the lowest energy sublevel you can have? Well, that's a 1s, first energy level S sublevel, right? How many electrons can I fit in a 1s? Well, 2. So let's say, for example, I've got 20 electrons. Am I going to be able to cram 20 electrons into 2 spaces? No. So after I've got 2 electrons in that 1s, it's full. So where's the next electron going to go? Well, it's going to try to find the next lowest energy sublevel, and it's going to go there. And then once that fills up, we'll go to the next lowest, and so on and so forth. So it's, yeah, really similar to parking cars, only you're not parking electrons. They don't actually pull into a space and stop. It would be really nice if all my 1s, energy level 1s, were below my energy level 2s, and all my 2s were below my 3s, and my 3s were below my 4s, and my S's were lower than my P's and D's and L's, and so on and so forth. It'd be really nice if it worked out that way. It'd be a lot easier. Do things ever work out easy in chemistry? They don't seem to, right? So what we have to do is we have to generate that order of filling somehow. So how are we going to do that? Well, here's what we're going to do. We're going to draw ourselves a little chart. So that's what we got over here on this side of the paper. So we got our 1s here. Okay, can I have a 1p? No. Only energy levels 2 and higher can have a p. You know, it all goes back to the rules. You know, when L is equal to 1, then the only allowed value goes from 0 up to n minus 1. So L equals 1, or rather n equals 1, L equals 1. I can't have an L equals 2. Can I have a 2s? Yes. Can I have a 2s? Can I have a 2p? Yes, I can have a 2p. You know, when n is equal to 2, L can be either 0 or 1. See, up to n minus 1. See, look, when we're talking about 2p, 2s, all this stuff, basically it's just the first two quantum numbers. This is my energy level, 2. This is my sublevel. This is n. This is L. Okay. Can I have a 2d? No. When n is equal to 2, L can't be equal to 2. It can either be 0 or 1. Can I have a 3s? Sure. Can I have a 3p? Yeah. Can I have a 3d? Yes. Can I have a 3l? No. Are you seeing a trend here? See a pattern? Notice that each successive energy level has one more sublevel than the last one did. Okay? And notice I've lined up all my S's, I've lined up all my P's, my D's, my L's, my G's, my H's, and my K's. All right? Do you see that? Can you generate something like this on your paper? Good. Okay? Side note, how many electrons can I fit in an S? 2. So how many electrons in the first energy level? 2. How many can I fit in an S? 2. How many can I fit in a P sublevel? 6. What's 2 plus 6? 8 electrons in the second energy level. How many can I fit in an S? 2. How many in a P? 6. How many in a D? 10. What's 2 plus 6 plus 10? 18 electrons in the third energy level. Is this following this little 2n squared formula that I gave you earlier? It is. 2 electrons in the first energy level, 8 in the second. See? It's just that now what we've done, instead of saying there's 32 electrons in the fourth energy level, now what we're saying is, yeah, there are. 2 of them are in the S sublevel, 6 are in the P, 10 are in the D, and then, of course, how many in the F? 14. I think it's about 4 each time. That should add to 32. That's where those 32 electrons are. So see, we're kind of narrowing things down here instead of just saying they're out there somewhere. Okay? So again, it is consistent. You do have a fighting chance of learning this. I didn't say it was easy, but I did say it was consistent. Okay, so we've got our little chart drawn here. So here's what we're going to do. We're going to draw diagonal arrows through the little chart, just like this. And then what we're going to do is we're going to start with the first arrow. We're going to write down every sublevel we go through. And then we're going to go through the second arrow. And then we're going to go through the third arrow and just keep writing things down. And when you do, you should actually have the order of filling. So let's see what we end up with here. So here we go. 1s, and then 2s, and then 2p, 3s, and then 3p, 4s. And that's this right here. Now notice so far all my 3s are below my 4s, my 2s are below my 3s, my 1s at the bottom. Everything's working out just great. This is the way it should be. What comes after 4s? 3d. You mean a 3d is higher in energy than a 4s? In reality, they're actually pretty close to the same. But by convention, we normally, especially when the orbitals are empty, your 3d is actually slightly higher in energy than your 4s. How can something in the third energy level be higher in energy than something in the fourth energy level? Well, unfortunately, it's because my parking lots for my electrons are not separate, distinct parking lots. What happens sometimes is my parking lots tend to kind of merge on me here, and that makes things more complicated. So it's kind of like that parking lot over by the science faculty and maybe the health sciences. You know, those lots just kind of merge together, and you can't really tell where one ends and one begins and all that. Unfortunately, that's what you run into. Here's a great example, and this was actually it's actually given to me by a student. I thought that is a really wonderful way of thinking about it. So let's pretend like you're going to a parking garage. You ever been to a parking garage? Sure you have. Okay. So you pull into your parking garage, and of course you've got floors here for your parking garage. Where you want to park? Well, you want to park on the ground floor, right? You have to walk down the stairs to get out of there. Well, but let's say, for example, you go on the first floor, and the first floor is completely full, no spaces. What am I going to do now? Well, you go to the second floor, and you'll look for a space. What if there's not a space there? Well, you go to the third floor, right? And you just keep going up floors until you find yourself a space. You don't drive to the roof because that would be too far down to walk. You may end up on the roof. You never know. But yeah, you always try to find a space on the lowest floor you can. All right. So let's say you find two spaces in this parking garage. There's a space over here on the third floor, and there's a space up here on the fourth floor. Which one of those is a better space? Well, I would probably park on the fourth floor here. Why would you want to park on the fourth floor when there's a space on the third floor? Because I'm closer to the stairs. See, I don't have to walk all the way over here to get to the stairs to get out. Well, that's kind of what's going on here. A 3D orbital or sublevel is higher in energy than a 4s, even though 3 is lower than 4. Because a D sublevel is so much higher in energy than an S, it overwhelms the fact that 3 is less than 4. So it's kind of like, ideally, you know, where would I rather park, on the third floor or the fourth floor? Well, third floor on average is better than the fourth floor. But is every space on the third floor better than every space on the fourth floor? No. Depends on how far we have to get to the stairs. How high you are up off the ground is N. That's your energy level. How far you have to walk across to get to the stairs is kind of like L. So, generally speaking, an electron in the third energy level is lower in energy than an electron in the fourth energy level. But the energy level is the main factor that determines the energy of the electron, but it's not the only factor. The sublevel has a small say as well. And in this case, the D is so much higher in energy than the S, it overwhelms the fact that 3 is less than 4. In reality, they're pretty close to the same. All right, but but yeah, by convention, especially when the orbitals are empty, we write it with the 3D higher than the 4s. Okay, well maybe that's just a fluke. Okay, well, let's continue on. So what comes after 3D? Well, 4p, 5s. Okay, we're back to normal. Everything's going good. What's after 5s? 4d. See, here we go again. 4d is higher in energy than 5s. Okay. 5p, 6s. What comes after 6s? 4f. Look, here's an orbital that belongs to an energy level 2 levels lower, but it's higher in energy, that sublevel is, than the 6s. Because an F is so much higher in energy than an S, it overwhelms the fact that 4 is less than 6. What's after 4F? Well, 5D. Okay. Then we're back to 6P. Okay. Then we go to 7S, 5F, 6D, 7P, 8S. Do you see, the further up I go, the more things tend to get messed up? That's the way it works. So there's two ways you can go about this. You can either memorize this, which I highly recommend you don't try to do, or you can draw yourself a little chart here and draw the arrows through, and you can generate this, which I think would be a whole lot easier way to go. All right? But one way or another, this is your order of filling. If you don't have this, you can't do anything that we're going to do in the next video. You've got to have the correct order of filling. All right. And again, the higher up you go, the more it gets messed up, so you can't just memorize it. One way you can deal with it is this way. Sometimes you can find little tricks sometimes to get things. And this works. Now, could I go up higher than 8s? Yes. I could go up to infinity, technically. but there's a practical limit to how high you need to go. All right, and that practical limit at this point is 8s. If you can make it up to 8s, everything that we do, you're gonna be just fine. Why is it 8s? We'll talk about it when we get there. All right, but that's good if you can make it up to there. All right, and that's how you generate the order of filling. Okay, well, there's my order of filling. Now that we know that and we know something about our 4 quantum numbers, now we can actually start writing electron configurations for atoms. So all this has kind of been building up to this. How are the electrons arranged around an atom? Well, I guess that's probably a good place to start the next video. So we'll do that. We'll talk about what all that means, and then we'll go from there. So good place to stop. We'll see you in the next video. Bye.